we have discussed the weighted summer circuit, which is a type of op-amp configuration that we can do addition for input signals weighted by the resistor values. So now we will do an example problem to practice this in example 2.7, and the prompt says we design a weighted summer circuit such that the first condition, V out is equal to negative V1 plus 5 VF, this relation of addition, such that the maximum output voltage, V out, is 10 volts. And then the current in the feedback resistor does not exceed 1 milliamp. So these are the three criteria that we have to design this op-amp in this weighted summer. And generally speaking, the process of how this goes is we select the according to the resistor values for R1, R2, and RF to achieve these three parameters. So the thing is, we could look at the just look at this formula that we have derived earlier and just solve from there. But in my opinion, this problem is best approached from an intuitive understanding, just doing KVL and KCL until we find the answer. So to do this, we'll first start with recognizing the ideal op-amp approximation. So assuming it's an ideal op-amp, we can say that the voltage here at V plus is equal to the voltage here at V minus is both 0 volts. This is because according to the ideal op-amp approximation, there is a virtual short circuit across the input terminals of the op-amp. So let's just write that down really fast. So V minus equal to V plus equal to 0 volts. This is called virtual short circuit. In this case, it is the example of virtual grounding. So then we can do the KCL now. So I'm going to define the current that goes through V in 1, call this V, let's call this I1. And I'm going to define the current go to input at V in 2, we're going to call this I2. And the combination of I1 I2, we're going to call this I. That is the summation of I1 and I2 joined together. In the case of the ideal op-amp, we know that the no current goes into the op-amp at the input terminals. So because of that, I is also the same current that flows through and into this RF, because there's no current going into this V minus. So using these things that we know about KCL, we can see that we're going to do the KCL on this node here, this V minus node. So KCL at V minus. In this case, we can see that I1 is going into the node, so I1 has a minus sign. And likewise, I2 is going in, so it also has a minus sign. And then the I is going out, so it has a plus sign. KCL says the summation of all the currents go to the node is 0. So we just rearrange, solve for I is equal to I1 plus I2. In this case, we can also represent I1 and I2 relative to the input resistor. So I is equal to I1 plus I2. Let's look at I1. So I1 is equal to this voltage minus this voltage divided by this resistor. So it is V in 1 minus 0 divided by R1. Now we have to plus I2. I2 likewise, same thing. It is this voltage minus this voltage divided by this resistor. So it is V in 2 minus 0 divided by R2. Now what we do next is just rewrite to be a little bit better. So just V in 1 divided by R1 plus V in 2 divided by R2. So this is the first relation that we will hold. And then we can do KVL. So we can see that this V out is equal to this voltage plus the voltage drop across this resistor. But we define I as going this way, so we should put a minus sign in front of that voltage drop across the RF resistor. So let's do KVL. So we say V out is equal to this voltage plus the voltage drop across there, except the current is going in the opposite direction. So it's going like 0 this time, because the current is going the opposite direction, is minus IRF. So we just rewrite this better. V out is equal to negative RF times I. So we can see we can plug this go into here. So V out is equal to negative RF V in 1 divided by R1 plus V in 2 divided by R2. So this is the input-output relation. Okay, so let's recall from the prompt that says when we design this circuit, we need to design the circuit such that well, first it says that maximum output voltage is 10 volts. So let's just set the V out is equal to 10 volts. Just do that for now. And also the maximum current go through the feedback resistor, which is just I. We say that is it says does not exceed 1 milliamp. So let's just set that equal to 1 milliamp. And I'm not saying that this is the correct value, but for this kind of problems, we just set the value first, then we solve, and then we see if the solution is feasible. So this is just the first guess that we make initially. We can just take these values. So V is equal to IR, right? So then you really just rearrange V equals IR to say R is equal to V divided by I, right? So RF, we can calculate that is equal to V, which is 10 divided by 1 milliamp. So RF is equal to 1 kilo ohms. We have solved for RF, but this is a tentative solution. What we need to do is we need to solve all the values first and then see if that solution will be feasible. So we just have RF equal to 1 kilo ohms just as an initial. Okay, then in addition, we are also told that to design this weighted summer circuit, we need to have that V out is equal to negative V1 plus 5 VF. So let's utilize that requirement now. Okay, so I'll just write it here. So V out is equal to negative V1 plus 5 VF. So we have this condition to solve for. But we also previously solved for the relation of the input and output here. So let's compare some things together. So these are the two things we have solved so far. And what we can do is we can compare some terms here. So you can see that this is just the -1 on here, so comparing terms. And then this is also a +1 on here. And then this is a 5. So we need to find some values for R1 and R2 such that they fulfill this addition requirement. So with the RF being 1 kilo ohms, we can just solve for this V out is equal to -1 kilo ohms times V in 1 divided by R1 plus V in 2 divided by R2. So we can see that in front of the V1 is supposed to be a +1. So therefore R1 should also equals 1 kilo ohm, and it will just cancel out. So we can say R1 is equal to 1 kilo ohms also. And then we can see that the V in 2 divided by R2, it needs to have some kind of 5. So we need to find a way to cancel out this 1 kilo ohms, but also have a multiplication of 5. A possible value for this is 1/5 times 1 kilo ohms. That means that R2, maybe, we don't know exactly yet, but maybe it's 1/5 kilo ohms. Okay, so we have solved for some values for R1 and R2 and RF, but we need to verify that this solution that we have proposed is a valid solution and it works. So to check for this, what we can do is we take V out is equal to negative RF, right? So it's -1 kilo ohms times it by V in 1 divided by R1, so 1 kilo ohms, plus V in 2 divided by 1/5 kilo ohms. Okay, so simplify, the kilo ohms cancel, so it's just negative V in 1 plus the kilo ohms cancel, but then it's a divide 5. So you do double divide, 1/1/5 is equal to 5. Okay, so this is the result, and it is consistent with here. So we have solved this problem. So in the next practice problem is 2.8. It is asking to use the advanced weighted summer circuit to provide this additive summation relationship across the inputs. Now, how can we approach this problem? We have looked at the advanced weighted summer circuit before, and there is a reason why I did not go through the derivation of how did we arrive at this advanced weighted summer formula, because it is very complicated and time consuming. But what I said was superposition would be the method of how we can solve this. But in the interest of saving time, this is because this circuit's more complex, we just take the formula and then we're just going to solve the practice problem directly. So I'm going to copy this formula for the advanced weighted summer, and I'm going to bring it down. So this is same circuit topology as our problem here. It's basically the same, but we just have a little bit less inputs instead of like having more than 3. So actually in the the formula, it's having 4 inputs, but here we are having 3 inputs, but we just use the same formula. So here is the formula, we just copy to here. Now the thing is that in this advanced way to assembly circuit, we need to make some modification to the formula so that it works for just the 3 input case. So that's simple, we just erase this V in 4 term. So now it's just 3 inputs relationship. So okay, so we are asked to design the circuit to this summation relationship. So we can see that in front of the 2, so I'm sorry, in front of the V1 there's a 2. So I'm going to denote that this coefficient here is 2. And then likewise in front of the V in 2 there is a 1. So this coefficient, okay, this coefficient denotes 1. And then in front of the V3 there is a negative 4. So this coefficient denotes negative 4. So now let's look at the intuitive understanding of what is going on in this circuit. So at the first stage of op-amp, it is V1 multiply 2. Here, just this thing here, okay? And then at the second stage of the op-amp, so second stage of op-amp is just Vn2 times 1. So this is the plus Vn2 plus V2 actually. You call this V2 plus 1. Sorry, 1 times V2. Okay, and then at the very ending, when we look at the include the feedback in the R3 and everything else, there's a minus 4 in front of V3. So we just put a minus 4 V times V3 here. So this is the circuit. More intuitive understanding is what's going on through each stage of op-amp. Okay. So how can we, create the resistors, find the values of all the resistors and the feedbacks and all these things? There's so many resistors here. So actually there's 6 different resistors values. So how can we solve this? Well, just like in the previous practice problem, we pick a initial value for a resistor and then we try to solve for everything accordingly, and we see if our guess was a valid solution. So let's start with taking RA, which is because RA is the first feedback. So let's just work with that, then see what happens. Okay, so RA, and you can pick any value you want for RA. The textbook starts with picking this to be 10 kiloohms initial guess. So we'll just follow that and work along with here. Okay, so we know that from this additive summation circuit formula, we can see that RA, this thing's here. So RA over R1 times RC over RB, we know this has to equal 2. Next, for this V in 2 term, we know is RA divided by R2 multiply RC divided by RB, this is equal to 1. And then for the V in 3 term, there is already included this minus sign from the formula. So we can say RC divide R3, this is equal to 4. With the initial guess of RA is equal to 10 kilo ohms, then we can say that R 10 kilo ohms divided by R1 times RC over RB equal 2. Next, we will look at we will plug in RA for the second term is also 10E3. So now we do divide by R2 times RC over RB is equal to 1. And finally, RC over R3 equal 4. So now we have three, actually we have, three equations here, and we need to still achieve more simplification. What's really interesting is that RC is present in all three equations. So that's a little bit interesting, because if we ignore RC, we can see what else is to eliminate. So let's just look here. There's a RC here, and there's a RC here, and then there's a RC here. So I'm just going to make this initial guess really fast. And this is what the textbook does. It makes this guess to see if set RC is equal to RA, which is, we made the guess before with 10 kilo ohms. Now, how did the textbook come to this guess? It's actually kind of interesting. What they noticed was this first equation here, this first equation here is double the equation here. So, and then there's the same, it repeats this RC over RB term. So that term is the same. The only difference is that we're having an R1 here, but we're having an R2 there. So then they were able to conclude that it is not the RC and the RB that is changing from this 2 on the first equation and the 1 on the second equation, but rather RB has to be half. R1 has to be half of R2, because this is present in both equations, but then here's double of here. So to write that out, we say, well, how we came to this guess, right? So that is moved down there. So R1 is equal to 1/2 times R2. So then, holding all else equal, in that case, RC would have to be the same, because this term here is the same as this term here. So they, using that information, they just make the guess. Says RC is equal to RA, which is 10 kilo ohms. So RC is equal to 10 kilo ohms. Okay. Another thing is that well, to repeat what we have been doing is we plug in the 10 kilo ohms for the places. So on this first equation is 10E3 multiply 10E3 divided by R1 RB is equal to 2. The second equation, 10 kilo ohms divided by R2 multiply 10 kilo ohms RB. And then the last one is 10 kilo ohms divided by R3 is equal 4. Okay, so we can solve for R3 now. So we know R3 is equal to so we just divide 10E3 divided by 4. So 10 kilo ohms divided by 4. So okay, we just solve for it. So it's R3 times 4 is equal to, like here, and then it's just 2.5 kiloohms. Okay, yeah, and then so we have solved for R3, RC, and RA. I think we can solve for R1 next. Yeah, because we talked about how R1 is just 1/2 of R2. So actually, in order to do that, we need to solve for R2 first. R2, and so let's compare. Oh, I forgot to write this is equal to 1. Okay, the only difference here and here is that the one contains R1, the other contains R2. So that means that R1 is equal to 1/2 times R2. And then we have found that RC is equal to 10 kilos. So plugging in for so plugging in for this like okay, it's up here, so just insert that to here. So 10 kiloohms times 10 kiloohms divided by 1/2 R2 RB is equal to 2. And then on the equation 2, it's 10 kiloohms divided by, just keep R2 times 10 E3 divided by RB equal to 1. So comparing terms, this is equivalent here, and then this is equivalent here. So the only difference is this 1/2 multiply in the front. So in order to cancel out this E3, this needs to cancel out 10 E3 divided by 10 E3, because then you'll be left with this divided by R3 right here, and then so because this 2 will cancel out with here to become 1. So in that case, we can conclude that R2, remember we're canceling out this 10 E3, so it's equal to 10 kiloohms. Okay, with that solved, we can now solve for R1, because we said that R1 is equal to 1/2 times R2. So R1 is equal to 5 kiloohms. And then yeah. Okay, so there's just one more thing we have not solved yet, I think. Okay, so we have R1, we have R2, R3, and we have RC and RA. One more thing we have not solved is RB. So just plug in everything that's remainder here. So it's 10 kiloohms divided by R2, which is 10 kiloohms. They just cancel as we talked about just now. Times 10 kiloohms divided by RB is equal to 1. So this cancel. RB is equal to 10 kiloohms. Okay. So we have solved for all the resistor values, but there's one more thing that we need to do, is we need to verify the answer, because we're basing our solution on the initial guess. So in order to do that, let's revisit the formula that we have up here. So I'm just gonna copy and paste to here, and we're going to revisit this formula. So V out is equal to V1 RA, as we have talked about. RA is 10 kilo ohms divided by 5 kilo ohms. Just write K for simplicity. RC we talked about earlier was 10 kilo ohms divided by RB is 10 kilo ohms plus VN2 RA is 10 kilo ohms divided by R2 is 10 kilo ohms. RC is 10 kilo ohms, and RB is 10 kilo ohms, and then the RC is 10 kilo ohms, and then R3 is 2.5 kilo ohms. Okay, so we solve and simplify. The coefficient in front of V1, this is cancelled to times 1, so then this is 2 here, so times 2 plus the V2 term, the coefficient, this cancel and this cancel, just times 1, and then the last one is, this is 10 divided by 2.5 is 4. Okay, so let me just rewrite to 2V1 plus V2 minus 4V3. Does this check with the question? And it does, so they match. So then we have solved. So we have solved for the resistor values. This concludes the discussion on the inverting configuration, so all the derivations and weighted summer circuit. And the next section talks about the non-inverting configuration for the op-amp.